Ready? Hello, everyone. We now start section 3.4 in the text. And really, we are going to talk mainly on moment-generating functions, which are discussed in section 3.4, but formal title of section 3.4 is just generating functions. And the reason is that we have numerous generating functions, and they are considered in this section 3.4, which is discussed on pages 162 to 170 of textbook by Evans and Rosenthal. And in particular, we have probability generating functions in definition 3.41 on page 162, which are good for non-negative integer valued random variables. And probability generating functions can be derived by a simple transformation from moment generating functions. Also, moment generating functions for which I use the acronym MGF are closely related to the concept of analysis. So it's a kind of advanced calculus known as Laplace transforms. So it's basically a Laplace transform of a negative argument. So I'll mention about it in the due course. And you already heard the name of French scholar Pierre-Simon Laplace before. Also, subsection 3.4.1 on pages 169 to 171 deals with the so-called characteristic functions. Which are more general than the MGFs. And in more advanced courses of probability theory, the emphasis is imposed on the studies of characteristic functions. However, what actually happens is in order to define the concept of a characteristic function, you need this imaginary one, so it's I, which is the root of -1. So in order to define the characteristic function, some know that I is just the root of -1. So it's a solution to equation x² + 1 equals 0. Some know more on the analysis of complex variable or complex analysis, which is a beautiful part of mathematics. Say math majors who take this course might find this subsection 3.4.1 being very interesting. Computer science majors might find it more challenging. So I should let you know that you are not going to be tested on characteristic functions and subsection 3.4.1 of the textbook, but if you're a pure math major interested in more advanced things, you of course are more than welcome to read subsection 341 and learn more on characteristic functions. And what happens that they always exist, whereas moment generating functions do not always exist. And it is customary for it's customary for calculus-based courses of probability theory taught in North America to use moment generating functions instead of characteristic functions. So we make an assumption that your distributions are such that moment generating functions do exist. I did not define them yet, but I'm going to do it later on. But I want to explain that there is a discrepancy between this section title and the title moment generating functions are used in the notes. I also want to say that for non-negative integer value distributions, so for non-negative integer valued random variables and distributions, there is a closely related concept of probability generating functions, which is more convenient for integer valued random variables. And there is nothing difficult about it, but it's a function obtained by a simple transformation from MGF. Therefore, I'm not going to pay that much attention to it, although it has its own range of applicability. And also, I should say that those of you who will study more advanced topics in mathematics might later learn of the so-called Fourier transform of analysis, which is analysis for some of you is the same as calculus. And Fourier transform of analysis is nothing else but characteristic function of probability theory. So again, this is what we borrow from analysis. Moment generating functions are closely related to Laplace transforms. MGFs is basically the same as Laplace transform with just negative argument. And characteristic functions discussed in subsection 3.4.1 is nothing else but Fourier transforms of analysis. So this stuff is the analytic probability theory. Section 3.1, I'm sorry, section 3.4 per se, it's on analytic probability theory. And in my own research in probability theory, I use a combination of direct probabilistic methods and also numerous analytical methods of probability theory. So I'm well familiar with these techniques, and I use it frequently in my own research. So of course, for some of you, this could be challenging. I will use numerous results of calculus, but of course, I will consider as many applications as possible. So the reason we use moment generating functions is, first of all, they generate moments of our distribution. So the other thing that we use them is because it makes it easier sometimes, not always, but sometimes, to identify particular distributions. For instance, it might happen that we should find the law of randomness. Of the cumulative error. So your error term is random. So it's your cumulative error, say a random variable x. But it's the sum of several components which are all random. And they might again, but they might or might not be independent, but say if they're independent random components, then it often happens that we could determine the law of randomness of the cumulative error comprised of independent random errors by using the techniques of moment generating functions. What is actually great about this function is that in the case of independent components, the moment generating function of such a sum of independent components simply equals the product of their moment generating functions. Again, this is the property that probability theory borrows from analysis. This is the property of Fourier transform and of Laplace transform. Okay, so we did not have to develop all this machinery from scratch. We borrowed the techniques from our colleagues working in analysis. Okay, and these are basically two main things for which we are going to use these moment generating functions. And of course, I will start discussing how to generate moments starting from this function. But first of all, I need to come up with the definition of a moment. So, the case moment of a random variable capital X taking about the origin, it's defined by E of X raised to the power K, where K equals 1, 2, etc. Okay, so it's the moment about the origin. We also say this is non-central moment or raw moment. We also have central moments that I'm going to discuss in a few minutes. So in particular, we have the first moment about the origin, which is expectation or AX or mu. Then we have the second non-central or raw moment, expectation of X squared. And then we have E of X to K, which is K's moment about the origin or K's raw moment. And this is really very basic thing. And when we discussed our gamma distribution, I even derived the formula for expectation of X to K for each representative of the gamma family. But we could also consider negative values of K. For instance, for K equal to -1, we can consider expectation of the reciprocal of our random variable 1 divided by X. So it's possible. We are not discussing how to do it, but it's possible, and it is sometimes used in statistical inference, we could also consider non-integer moments. Say expectation of x to the power 1/2 or expectation of root of x. And such moments are also used in statistics. There are so-called variance stabilizing transformations where expectation of the root is sometimes used. Okay, so such things are also possible. And if you are interested, you can, of course, ask me questions on such things. But for the main purposes of this course, we just consider positive integer moments of our random variable. Of course, they might or might not exist. But these are non-central or raw moments. There are also central moments. For instance, second central moment E of x minus ex squared is nothing else but the variance of our random variable. And we know that it equals expectation of x squared minus ex squared. Hence, there is a connection between central and non-central moments. Are actually like central moments very much, but tastes differ. Also, I should say that the third and fourth central moments which are E of x minus ex cube and expectation of the centered variable x minus ex raised to the power 4 are closely related to skewness and kurtosis of your distribution being considered. So the first two moments are the most important, of course. They're closely related to mean and variance, but third and fourth central moments are also quite important, being related to skewness and kurtosis of your distribution being considered. Yes. So, but anyway, you shouldn't have problems with the moment. So, case moment is expectation of a non-random power function of your random variable. And finally, the definition of moment generating function. So this is really the definition. MGF, a moment generating function, sub capital X of t, so where x is your random variable being considered, is by definition expectation of e raised to the power xt. So for each t, which is non-random, we get new random variable t times x, like expectation of it. To tx is a non-random function because it's expectation of a new random variable. Let me comment on that now. Okay. For a fixed non-random t, e raised to the power t times capital X, or exponent of t times x, is a new random variable. We can denote it by g sub t of capital X. Yeah, so it's a new random variable where gt of u is e to tu, is a non-random function. And then m sub capital X of t is expectation of this non-random function g sub t, where we replace argument u by our new random variable capital X. That's what it is. So it's expectation of a certain non-random function where the argument is a random variable and t is fixed. So for each t, we obtain a number. And then when we vary t, we obtain a function of t. That's what it is. So I already discussed how to find expectations of functions of random variables before. And when we had this discussion, I explained that it's, of course, sometimes possible to derive such expectations from scratch. However, there are shortcut formulas which work in continuous and discrete cases respectively. So in the continuous case, this expectation of a non-random function of a continuous variable can be evaluated as the integral from negative to positive infinity of this function e to xt times the PDF of the original continuous variable capital X dx. And of course, this interval of integration is not necessarily the whole real line. So, and in the discrete case, this is going to be the sum over all possible values of x from the support of our discrete random variable of e to xt times the PMF, p sub capital X of argument little x. Okay, and I stress that this is the definition, and these are the shortcut formulas which enable us to evaluate such an expectation of a non-random function of a random variable for each fixed t, and then t becomes an argument itself. Okay? And of course, you can derive the probability distribution of this new random variable g sub t of capital X for each t and evaluate then its expectation, but it's not advisable. Yes, so we use these two shortcut formulas for continuous and discrete cases respectively. So I want to bring up a few issues. First of all, moment generating functions may or might not exist for all t, except t equal to 0. So, but they might exist for some t, but not for all t. But for t equal to 0, it's always the case. So, but it might happen that moment generating function does not exist for any t except 0. And let me consider such counter example. So such a counter example is our Cauchy distribution considered before. The PDF little f of argument x is 1 over pi times 1 divided by 1 plus x squared, where x is between negative and positive infinity. So obviously, integral from negative to positive infinity of e to 0 times x, f of x dx is 1, because this is the total probability. Yeah, e to 0x is 1. Yeah. But then, when we consider any other t, so if t is not equal to 0, so we have such an integral from negative to positive infinity of e to tx times 1 over pi times 1 over 1 plus x squared dx. So we have such an integral. And then for positive t, e to tx grows much faster at infinity than 1 plus x squared. So therefore, this integral equals positive infinity for t greater than 0, and for negative values of t, you realize then you have a problem, at negative infinity, because when t is negative and x goes to negative infinity, it's going to be a positive number, and it's also going to be blowing up there. Yeah, so therefore it's also going to be positive infinity for negative values of t. So it's 1 or positive infinity, which is not good. So here we say that no MGF. But a good thing for us is that for most distributions considered in this course, like for standard distributions, moment generating functions exist. And they're given in closed form, which is in the table provided. Okay? So how you also can find it in the book. And you remember we considered Pareto distribution, which also has the behavior being negative power of x as x goes to positive infinity, but it's only positive for x greater than 1. So moment generating function is going to be defined for negative values of the argument, but not for positive values of the argument t. So therefore, moment generating function does not always exist for all the values of t, even if it's in the closed form. Yeah. So really, what matters is the formula for moment generating function at a certain neighborhood of the origin t equal to 0. So, and we will consider numerous examples of this nature in the due course. So next, we'll discuss how to generate expectation, the second non-central moment, the third non-central moment, etc., starting from our moment generating function that was already rigorously defined. But moment generating functions are fingerprints of your probability distribution. And there is a remarkable result known as the uniqueness theorem. That's actually what we also borrow from analysis. And this result is given as theorem 3.4.6 on page 167 of the textbook by Evans and Rosenthal. It's known as the uniqueness theorem. So there is one-to-one correspondence between a particular probability distribution and its moment generating function if such a moment generating function exists. And this actually gives us a good motivation to find them, because it might sometimes be easier to calculate the moment generating function of a certain function of a random variable or function of random variables. And it might happen that such a moment-generating function of a certain new random variable can be recognizable. So it might belong to the class of moment-generating functions of particular distributions that is already at our disposal. And then if this happens, and I'm going to provide numerous illustrations of them, that we could use it together with the uniqueness theorem 3.4.6 to identify our distribution. So if you find that MGF of what we obtained is MGF of a particular probability distribution that we already are aware of, then we are fine. We can say that what we obtained is distributed according to such and such probability law, which is justified by such a beautiful uniqueness theorem. So I should say that illustrations would be the sum of independent normal random variables, the sum of independent Poisson random variables, the sum of independent gamma random variables, and the sum of independent binomial random variables. So we'll consider at least 4 illustrations of this important observation. So basically it suffices to find moment generating function and identify it and then switch backwards to a particular distribution if it belongs to the class of non-moment generating functions. And now I want to discuss some results from calculus. So it's a calculus theorem. If you have a certain power series, then it may be differentiated or integrated termwise, and the result would be another power series with the same radius of convergence. Okay, so we also have numerous Fubini type results on the interchange of the order of summation or the interchange of the order of summation and integration. So I want now to explain why we use such a name, moment generating function, and show how they generate the moments. But first of all, let me remind you the Taylor series for our exponential function e to y at 0. So it's going to be the sum of a k from 0 to infinity of y to k over k factorial, which is 1 plus y squared over 2 factorial plus y cubed over 3 factorial plus etc. So by definition, MGF is the expectation of e to the power capital X times t. And in the continuous case, which I consider now for simplicity only, it's integral from negative to positive infinity of e to xt times the PDF little f sub capital X of x dx. And then for this exponential function, I use its Taylor series representation. So it's convergent, so it's over there, but y is here, it must be x times t. So therefore, I get such an infinite series over k from 0 to infinity of xt to the power k over k factorial. And then it's multiplied by the PDF f dx and integrated from negative to positive infinity. And then I may interchange the order of integration and summation. Hence, it will be the sum over k from 0 to infinity of integral from negative to positive infinity of xt to k over k factorial times the PDF little f sub capital X of little x dx. So what I can do here is recognize that t to k is just a multiplier that does not depend on the argument x of integration. Hence, I can factor out t to k. And I also can factor out k factorial. So therefore, this integral will be t to k over k factorial times the integral from negative to positive infinity of x to k times the PDF f of x dx. And this inner integral within the parentheses is nothing else but the expectation of x to k. So I get it here. Hence, what I obtain is that it's the sum of k from 0 to infinity of expectation of x to k times t to k over k factorial. And hence, what I realize is that moment generating function is just an infinite series where we have t to k over k factorial, and the coefficients are non-central moments. So hence, if we consider the Taylor series for our moment generating function at 0, we get these coefficients, non-central moments. Hence, the derivatives of MGF at 0. That's the observation that is very important. And hence, in order to generate non-central moments, we simply need to find the corresponding derivatives of our moment generating function and then evaluate them at the origin. That's the end of the story, and that's what justifies the name for our function. And a bit more of calculus. Yeah, it's, I know, boring, but this is a methodological problem with probability theory that numerous results of probability theory are making perfect intuitive sense, but proving them is sometimes a challenge because we need to use a lot of sophisticated results of calculus. So, and it's one of such examples here. So please be patient, but also it gives you an opportunity to review some results of calculus that you already learned by now. Okay, let's just see what we get. So our MGF is such a Taylor series. So it's the sum over k from 0 to infinity of e to x to k times t2k over k factorial. So we'll write it in a long form. It's 1 plus the expectation times t plus the second non-central moment times t squared over 2 factorial plus the third non-central moment times t cubed over 3 factorial plus etc. Let's find the first derivative. So we differentiate term-wise. So the derivative of 1 is 0. The derivative of e of x times t is just e of x. The derivative of this third term is this constant e of x squared times 2t, which is derivative of t squared over 2 factorial, etc. And then what we obtain when we evaluate the first derivative at 0, so we get 0, then you have 2t as the derivative of t squared, so at 0 it is 0. The derivative of t cubed at 0, I'm sorry, the derivative of t cubed is 3t squared, but again it's 0 at 0. Therefore, this term and all subsequent terms become equal to 0 at 0. And what remains is just the expectation of x. Hence, the expectation of x is nothing else but the first derivative of MGF at 0. And it gives you an algorithm of evaluating the expectation. Find MGF and differentiate it and evaluate the first derivative at 0. Sometimes it's easier said than done, but there are examples, for instance, it's the case for the geometric probability model, where it is easier to find moment generating function and then differentiate it to find the moments, rather than finding moments from scratch by evaluating the infinite sums. Okay? So let's talk about the second moment. So the second derivative of our MGF, mx double prime of t, equals the derivative of this function. The derivative of 0 is 0. The derivative of e to x is also 0. It's a constant. Then we have this term expectation of x squared times the derivative of 2t over 2 factorial, which is going to be 2 over 2, or 1. Therefore, the derivative of this third term is expectation of x squared, or the second non-central moment. And then the derivative of all the subsequent guys will be certain positive powers of t, and hence they are all going to be equal to 0 at 0. Hence, the second derivative of MGF at 0 is the second non-central moment. And what actually happens is that we obtain that variance of our random variable can be evaluated as the second derivative of MGF at 0 minus the square of the first derivative at 0. And of course, it should be non-negative. So, and to get k's non-central moment, we need to keep differentiating of our MGF k times with respect to this argument t, and then set the value of t equal to 0. So it might be long, but this method is going to work. And let's talk about our Poisson probability model. So we have Poisson distribution with parameter lambda greater than 0. And So what we obtain is, this is the discrete case. So MGF, which is expectation of e to xt, is the sum over little x from 0 to infinity of e to xt times this probability mass function e to negative lambda times lambda to x over x factorial divided by, yes, so we have it here. But then what we have e to xt and lambda to x. So they can be combined, and these two factors can be written as lambda times e to t raised to the power x over x factorial, and e to negative lambda can be taken outside. And when we look at this infinite series over x from 0 to infinity of this constant lambda times e to t to the power x over x factorial, this is nothing else but the Taylor series for the exponential function around 0. Therefore, it's going to be the exponential function of this argument lambda times e to t times e to negative lambda. Hence, this can be rewritten as e to the power lambda times e to t minus 1. And this moment generating function for the Poisson distribution exists for any value of argument t. Isn't it nice? And I already proved before that expectation of a Poisson distribution equals the value of Poisson parameter lambda. But we are going to rederive it by using this observation that expectation is the first derivative of the moment generating function at 0. So let's differentiate our function. So MGF is e to the power lambda times e to t minus 1. So we need to differentiate this function, and we use the generalized power rule, or chain rule. So the derivative of exponential function is exponential function, but we need to differentiate the argument, so we need to multiply by the derivative of lambda times e to t minus 1, which is clearly lambda times e to t. And we can rewrite it as lambda times e to lambda times e to t minus 1 plus t. In order to find the expectation, we need to plug in 0 for t. So when we plug in 0 for t, it's going to be 1 minus 1, which is 0. Hence, this guy is also 0. Hence, it will be lambda times e to the power 0, which is 1. Hence, the expectation is lambda. As simple as that. So now the second derivative. So we need the second derivative in order to find the variance. So the second derivative is the first derivative of the first derivative. So we don't differentiate lambda, we differentiate m prime of t. So again, we use the chain rule. So we have this multiplier lambda times this exponential function times this derivative of lambda times e to t minus 1 plus t. So when we differentiate this power, we get that it will be lambda times e to t, negative 1 disappears, plus 1, which is the derivative of t. And we can rewrite the second derivative of MGF as e to the power lambda times e to t minus 1 plus t times lambda squared, lambda times lambda is lambda squared, times e to t plus lambda. And only here we plug in the value of t equal to 0 in order to get expectation of x squared or the second non-central moment. So when we plug in 0, so this guy becomes 0, and it's going to be e to 0, which is 1. Here we have lambda squared times 1 plus lambda, and hence our second non-central moment is lambda squared plus lambda. And what remains is to use this formula for the variance, being expectation of the square minus the square of expectation. And in terms of MGF, it's written like that. It's always to be non-negative. So if you get that such a difference is negative, then be sure that you screwed up the things. Yeah. So, but anyway, we obtain the variance as the difference of lambda squared plus lambda minus the square of expectation, which is lambda squared, and hence the variance is also lambda. It's possible to derive it from scratch by evaluating expectation of x squared the long way, but I hope you realize it's nicer and simpler to use these analytical techniques of moment generating functions. So the conclusion which we make, and that's what I mentioned, is that variance for the Poisson model is the same as the expectation. We say that the Poisson model is equi-dispersed. Which means that for each Poisson distribution, expectation is the same as the variance. They're both equal to the value of the Poisson parameter. This is a great property of the Poisson model, which makes it very simple. However, the property of equidispersion is not what usually the data sets which occur in real life and applications exhibit. Usually the models which we observe, the distribution for counts, they're over-dispersed. Usually variance is bigger than the mean. And it's one of the pitfalls of the Poisson model if you try to apply it to any situation where we deal with count data, the data for non-negative integer observations. Usually they're over-dispersed, but for Poisson model, we get equidispersion. It's still great to have such properties. And I should say that there are other equidispersed distributions. So if you're interested, I can provide you some references to my lectures, say in February 2015, I gave a talk at Toronto Probability Seminar on St. George campus, where I spoke about other equidispersed distributions, among many other things. And now, I want to discuss some more subtle and very useful properties of moment generating functions. So I'll also discuss them in more detail on slides 18 and 19 of this lecture. First of all, if we consider a new variable, ax, which is just a random variable x multiplied by constant a that can be positive or negative, MGF of such transformed variable can be derived from the MGF of the original variable, capital X, but we simply need to evaluate it at argument little a times t. I'll prove it later on. And if we add a constant, if we shift our random variable, then moment generating function of a constant plus our random variable is this factor e to at, where a is our constant, times MGF of the original random variable capital X evaluated at point t. So it's a useful property. And then we have this multiplicativity property, which I already mentioned before, that if random variables x and y are independent, then moment generating function of their sum equals the product of their moment generating functions. And this multiplicativity property of MGFs is given as theorem 3.4.5 part B on page 166, and part A of theorem 3.4.5 is the analogous property for the probability generating functions. So I encourage you to read about properties of probability generating functions yourselves. I just simply cannot consider all generating functions in my lectures. But they're straightforward, and they're actually for non-negative integer value distributions. They are more important than moment generating functions, and I use them a lot. So this is an important property which I mentioned before, but such a multiplicativity property is what we borrowed from analysis, and I'm going to discuss how to prove this beautiful property later on. So then if we apply the induction argument to this multiplicativity property, so we can derive that if we consider n independent random variables, then moment generating function of the sum at point t is nothing else but the product of these individual moment generating functions of these random variables xi of argument t. So of course they might or might not exist. If they do not exist, really you ought to use characteristic functions of Fourier transforms and deal with complex numbers, but it's going to be a headache for many of you. Therefore, we impose a condition that MGFs of individual terms, xi's here, do exist. So if they do not, we are not in position to apply this theorem, of course. So I would like to say that at the beginning of today's lecture, I spoke about importance of generating moments using the MGFs. And the other property is that we could identify our distributions by using the moment generating functions, which is due to the uniqueness theorem of the correspondence between distributions and their moment generating functions. So they have all the information about your distribution. And also, it should be said that getting expected values from the MGFs can be easier than the direct calculation. I showed how to find the first two moments for the Poisson distribution, but I also want to talk about the geometric model now. Because for the geometric model, it's not that easy to evaluate the expectation and variance from scratch by just using the formulas for these moments. Yeah. So let me show now how to find the expectation and variance for the geometric distribution by using these analytical techniques that employs moment generating functions. Okay, so our geometric random variable capital X with parameter theta from the unit interval is characterized by the PMF P of little x, which is probability that capital X equals little x and little x is equal to 0, 1, 2, etc. Is such that it's theta times 1 minus theta raised to the power x. And I already showed that this is a legitimate probability mass function, so the terms are non-negative, and the total sum is indeed equal to 1, and because what you get would be the geometric series, for which we know the sum. Okay, but let's find the MGF. Capital M sub capital X of little t is certainly the sum over x from 0 to infinity of e to tx times theta times 1 minus theta raised to the power x. And we need to evaluate this infinite series. So, of course, I can take theta outside the summation sign, and e to tx times 1 minus theta to x can be rewritten as e to t times 1 minus theta, all raised to the power x. And I derive another geometric series. Okay, so hence what we obtain is that m sub capital X of t is theta times the sum of x from 0 to infinity of 1 minus theta times e to t raised to the power x. Hence, it's going to be theta multiplied by the sum of this infinite geometric series, which is clearly 1 minus this base, 1 minus theta times e to t. And of course, we have a limitation. So here it should be, so this factor should be less than 1. So 1 minus theta times e to t should be less than 1. Hence, t should be less than natural log of 1 over 1 minus theta. Hence, this formula is going to be true for the values of the argument of our moment generating function smaller than the natural log of the reciprocal of 1 minus theta. For t greater than this guy, so for t greater than or equal to natural log of 1 over 1 minus theta, m sub x of t will clearly be equal to positive infinity. So we are in a situation that our moment generating function exists only for a certain region of argument t, but not on the whole real line. Okay, now let's differentiate this function. So m prime of t is, of course, this factor theta times the derivative of 1 minus theta to e to t to the power negative 1. So let me write it this way. So to the power negative 1 prime. And we again need to use the chain rule. Yeah, so what we obtain is that it's going to be theta times this negative 1, because that's how we differentiate the power function, times this negative sign, so another negative 1, times factor 1 minus theta, which is a constant, times the derivative of e to t, which is e to t. Times this expression to the power negative 2, or we just divide by this expression squared. So therefore, we have 1 minus theta e to t squared. And we need to do the cleaning. So hence it will be theta times 1 minus theta times e to t over this expression squared. So we got a neat formula. And in order to find the expectation, we just need to plug in 0 for t. So m prime of 0 is clearly theta times 1 minus theta times 1. And in the denominator, we have 1 minus theta times e to t squared. So e to t becomes 1. And it will be 1 minus theta, which is going to be theta squared. And the result is that the expectation is simply 1 minus theta over theta. Okay. That's the result that you find in the formula for the numerical characteristics of geometric distribution. What about the variance? So you need to differentiate the MGF again. So I leave it as an exercise for you to find yourselves. I'm just going to produce the result on the board. And by the way, I also should promote this method because I'm going to discuss why it's going to be a more efficient way to find the expectation and also the variance. Okay. So let's see what we should do by using the brutal force method. So expectation is going to be this infinite sum over x from 0 to infinity of x times theta times 1 minus theta to the power x. So theta, of course, can be taken outside. So for x equal to 0, it's of course 0. So it's going to be theta times the sum over x from 1 to infinity of x times 1 minus theta to the power x. And I bet that many of you will have a problem evaluating this infinite series. So it's much nicer to find the moment generating function, because for moment generating function, you just get the geometric series for which you know the answer. And then you get a nice function which you differentiate and get the derivative at 0. So it would be easy rather than finding this infinite series of x times 1 minus theta raised to the power x. And then find the second derivative at 0 yourselves. I should just say that m double prime minus theta, minus 1 minus theta over theta squared, which is ex squared. So that's what's going to be your variance, is going to be nothing else but 1 minus theta over theta squared. So, but please get this result yourselves by finding the second derivative of your moment generating function, or just the first derivative of your first derivative. So you simply need to take this moment generating function, which is theta times 1 minus theta times e to t in the numerator, divided by 1 minus theta times e to t squared. So you differentiate this ratio with respect to t and find the derivative at 0. So, and then you eventually get a neat formula for the variance of the geometric model. Okay, so that's actually a comment that MGFs can be often easy to deal with if you need to find the moments, but it's not always the case, say, for numerous other distributions. So brute force method might be faster. Yeah, and sometimes finding moment generating functions could be a real headache. Okay. And also, as I already said, that if you find moment generating function of a certain non-random function of your random variable or random variables, and you are able to recognize it as MGF from the table with specific values of parameters, then your problem of identifying the distribution is solved. And I want to proceed with particular examples. Yeah, so say for normal distribution and for chi-squared distribution, which we discussed before, I want to present the moment generating functions. And they are just like fingerprints of specific probability distributions. So say if your random variable is normal with parameters mu and sigma squared respectively, then its moment generating function is the exponent of mu t plus 1/2 times sigma squared times t squared. And since we have this uniqueness of correspondence between MGFs and the distributions, what actually happens is that if you obtain that for your distribution, moment generating function is the exponent of mu t plus 1/2 times sigma squared times t squared with particular values of mu and sigma, often, it might be often the case, then you should immediately recognize your distribution with your particular moment generating function to be a member of the normal class with specific values of parameters, which are the mean and the variance respectively. So it's if and only if condition. Okay? And for a chi-squared random variable, which is the sum of the corresponding number of squares of standard normal variable, as I'm going to discuss it in detail, and it's a special case of the gamma model with the shape parameter alpha equal to nu over 2 and the rate or scale parameter lambda equal to 1/2. Its moment generating function is 1 minus 2t raised to the power negative nu over 2 for t less than 1/2. So for t greater than or equal to 1/2, MGF is positive infinity. So again, it's if and only if condition. So if you obtain that your moment generating function is given by such a formula, then you should immediately identify your distribution as being a member of the class of chi-squared random variables. So I'm going to derive moment generating function of a gamma family in a few minutes. Okay? Okay. Yeah, but prior, I want to derive this formula for the moment generating function of general normal, but I'll only do it for now in the case of the standard normal variable. So I assume that mu is 0 and sigma squared is 1. Okay. So, proof for mu equal to 0 and sigma squared equal to 1. So our y is standard normal or capital Z. Okay, and see also theorem 3.4.4 on page 166 of Evans and Rosenthal textbook. So m z of t is by definition, or actually it's expectation of e to tx, but we use the shortcut formula for the expectation of e to tx, and hence it's integral from negative to positive infinity of e to tx times the PDF of standard normal or bell-shaped curve, which is 1 over the root of 2 pi, times e to negative x squared over 2 dx. And then, of course, I want to combine these exponents. But what I will do is I'm going to represent tx minus x squared over 2 as negative t squared over 2 minus it will be positive t squared over 2 minus x squared over 2 minus x over root of 2 times t over root of 2 times 2 plus t squared over 2. So, and if you check everything, you realize that my algebra is okay. Therefore, it's going to be t squared over 2. So I have t squared over 2 with positive and negative signs. And this is, of course, the weird way to rewrite x times t, but I have a good reason to have roots of 2 beneath x and t, and then it's multiplied by 2. But basically, it will be t squared over 2 minus x minus. So it will be minus x over root of 2 minus t over root of 2 squared or it can be also rewritten as t squared over 2 minus x minus t squared over 2. So therefore, these guys actually can be rewritten in such a form, and t squared over 2, so it will be with the exponent, it can be taken outside the sign of integral. So let me rewrite it in detail. So, therefore, m sub z of t is going to be integral from negative to positive infinity of 1 over the root of 2 pi times e to the power t squared over 2 minus x minus t squared over 2 dx. And e to t squared over 2 can, of course, be taken outside the sign of integral. And I will implement the change of variables y equal to x minus 2, and y is again between negative and positive infinity. Dx is the same as dy. So hence, this is going to be e to t squared over 2 times the integral from negative to positive infinity of 1 over the root of 2 pi times e to negative y squared over 2 dy. And everything is done already because this is equal to 1. So it's total probability for standard normal variable z is just rewritten in the other argument. But the value of the integral is well known. So I already spent a lot of time discussing why the bell-shaped curve is a legitimate probability density function, and therefore the total integral is 1. Hence, the MJF for standard normal is e to t squared over 2. So isn't it nice? So, and then I will derive the general result for an arbitrary member of the normal family later on by using particular results regarding linear transformation of my random variable. And since chi-squared variable is just a particular member of the gamma family with shape nu over 2, and nu is positive integer, it's the number of degrees of freedom, and lambda is 1/2. So I'm going to show how to derive MJF for an arbitrary member of the gamma family. Okay, so for random variable capital X being distributed according to gamma law with shape parameter alpha and rate lambda, where alpha and lambda are both positive, m sub x of t is not by definition, by the shortcut formula, it's going to be integral from 0 to infinity, because gamma PDF is positive only for positive values of x, so it will be integral from 0 to infinity of e to tx times the PDF, which is lambda to the power alpha over gamma of alpha times e to negative lambda times x times x to the power alpha minus 1 dx. And then what is tempting is to combine these two powers of exponents. So it's going to be e to negative lambda minus t times x, and we will have change of variables. Y equal to lambda. So it will be lambda minus t. But we want this to be positive because it should decay at infinity. So lambda minus t should be positive. And therefore, t should be less than lambda. In order for this integral to be less than infinity, in order for this integral to converge, the argument c should be less than lambda. Otherwise, we get infinite value of our moment generating function of the gamma family. Okay? Okay, so what we obtain now that mx of t for t less than lambda, of course, we are really interested in this case. It's going to be int. So we are going to factor lambda to the power of alpha outside, but we are going to keep 1 over gamma of alpha inside the sign of integral because we have a good reason to do that. So it's going to be lambda to alpha times integral from 0 to infinity of 1 over yeah, just a second. No, I don't really need this to be new variable of integration, but I'll just denote it by kappa. Yeah, so it will be kappa. So lambda minus t should be positive, so kappa should be greater than 0. So this is the Greek letter kappa. So therefore, I still have lambda to alpha times the integral from 0 to infinity of 1 over gamma of alpha times e to negative kappa times y, or kappa times x times x to the power alpha minus 1 dx. And what I want to do now is to multiply this guy by kappa to alpha and divide by kappa to alpha. So therefore, it's going to be lambda to alpha over kappa to alpha, where kappa to alpha is lambda minus t to the power alpha. And then it will be integral from 0 to infinity of kappa to alpha over gamma of alpha times e to negative kappa times x to alpha minus 1 times dx. And then I recognize this integral as the total probability for a gamma random variable with shape parameter alpha and rate kappa, which is positive. Therefore, this integral is 1. And I don't have to evaluate it from scratch. So it's total probability for a different member of the gamma family, but it's still 1. Therefore, what I obtain is that it's going to be lambda to alpha over lambda minus t to the power alpha, which may be rewritten as 1 over 1 minus t over lambda raised to the power alpha. And I got such a neat formula for a moment generating function of a general member of the gamma family. And then if I look at this special case where alpha is mu over 2, so this is exactly that, and lambda equal to 1/2, so instead of dividing by 1/2, I just multiply by 2, I indeed get this formula for MGF of a member of the subclass of chi-squared random variables with the number of degrees of freedom mu being an arbitrary positive integer. So these certainly nice functions, and let me provide the graphs for moment generating functions for various members of the normal family. So the symmetric case where mu is 0 and sigma squared is 1, it's standard normal. So you have such e to t squared, yeah? So, and then it, of course, grows towards infinity pretty fast at negative and positive infinity. So for positive mu, say this is corresponding to mu x1 and sigma squared is 1. So of course it's no longer symmetric, it's asymmetric, and it goes to positive infinity at positive infinity, but it will be mu e to mu t plus sigma squared times t squared over 2. Eventually, it will still go to positive infinity at negative infinity, but it will go down. Yes, so it will be actually yeah, it will be not symmetric. It will go down, but then eventually it will go up. And then for mu equal to -1, so you obtain that it will go up there much faster. And you can realize that these two curves are symmetric with respect to the vertical axis. Yeah, so they obtain from each other by changing the argument t for its opposite. So replace t by negative t, and you switch from one curve to the other one. So the second graph pertains to three specific members of the chi-squared family of distributions. So it's 1 minus 2t to the power negative mu over 2, and I have three such graphs corresponding to 1, 2, and 3 degrees of freedom. So what really happens here is that at 1/2, all these functions blow up, because you will divide 1 minus 2t by a negative power. Yes, so therefore, all these functions will have common vertical asymptote at t equal to 1/2. Okay, but The larger nu is, the steeper this function will increase to positive infinity when the argument approaches 1/2 from below. And I now want to discuss an important result which pertains to the sum of independent Poisson random variables. This is the result important for the arithmetic of probability distributions and also for applications in communication theory and in insurance. Say, if you have an insurance company that has customers in all the Canadian provinces, and you know, the idea of having as many customers covered as possible is that we spread the risk over all the insured drivers. Yeah. So the number of accidents per province is modeled by a Poisson variable, and we assume that these random numbers of accidents per a specific time period, say per year or per month, they're independent from province to province. Then what actually happens is that the total number of accidents is again Poisson distributed. What we need to do is just to add the intensity of the Poisson flow of arrivals. That's what we use. This is the terminology used. We have the accidents or events happening. This could be signals transmitted in communication theory, the job sent to the printer, etc. So if we share the printer with other customers. But this is the idea. If you have several Poisson flows and they're independent, then the cumulative flow is also Poisson, and you just need to add the Poisson parameters. That's what this result states. Namely, if you have n independent Poisson random variables x1, x2, xn with their own Poisson parameters lambda I, and we consider the sum capital Y, which is the sum of I from 1 to n of xi, then MGF is Poisson with the parameter equal to the sum of I from 1 to n of lambda I. What we need to do is just to add up the Poisson intensities. And this result is easy to prove by using the techniques of moment generating functions and this remarkable multiplicity property of moment generating functions, that for independent variables, moment generating function of the sum equals the product of their moment generating functions. So therefore, we end up with the product of I from 1 to n of e to lambda I times e to t minus 1, which is MGF of an individual Poisson variable with parameter lambda I. But the product of exponential functions is exponential function of the exponents. So that's it. So what we need to do is just to add up these exponents, and e to t minus 1 is a common factor. Therefore, what we need to do is just to add up lambda i's, and they are multiplied by this common factor e to t minus 1. But when we look at this expression, we identify it as the moment generating function of Poisson random variable with parameter lambda 1 plus lambda 2 plus etc. plus lambda n. And due to the uniqueness of correspondence between moment-generating functions and their distributions, we get that the sum of Poisson variables, provided that they are independent, is again Poisson with this cumulative intensity. Cumulative intensity is lambda 1 plus lambda 2 plus lambda n. So you just cannot overestimate how important this result is for applications. And I want to say a few words about the theory. So this is really if and only if result. Say a Poisson random variable can only be decomposed into Poisson components, provided that we want them to be independent. There is such nice if and only if condition. This part is straightforward, so just straightforward property of the exponential function. The converse is known as Rykov theorem. I believe it was proved, or actually it was published in 1938, and it's an important result of arithmetic of probability distributions. You'll see other apples from the same apple tree. Namely, we'll discuss Cramer's theorem about decomposition of normal random variable, and also Cochran theorem on decomposition of chi-squared variable. I worked in this area of arithmetic of probability distributions, and actually in 2004 I proved a general theorem on such decomposition that incorporates Rykov, Cramer, and Cochran theorems as special cases of my result. Okay. Let me now discuss this property which I already presented before. Yeah. So if random variable x has moment generating function capital M sub x of t, and little a is a certain non-zero constant, then moment generating function of such transformed random variable a times x at argument t is moment generating function of the original random variable capital X evaluated at argument at. So this is not that hard to derive at all. So in ax of t, so this is the proof. So it's expectation of e to t times ax, and I just switch the parentheses. So, and this is of course the same as expectation of e to at times x. And when I get this representation, I identify it as moment generating function of the original variable x, evaluated at argument at, and that is the end of the story. And at the beginning of next lecture, I will discuss how to use this remarkable result in order to derive an important scaling property for the gamma family. Thank you, and see you next time.